Let's now look at our fourth example in this video lesson. So example 4, reading it out, we see that in a sample of 423 cell phone users, shows 321 of them are iPhone users. At significance level 0.001 is the sample showing strong evidence that proportion of iPhone users is other than 50%. And so at this point, after doing repetitively about 3 examples prior to this example, then we can see that our first responsibility, again, is to recognize the 2 hypotheses. H0 for the null hypothesis and H1 is for the alternative hypothesis. And we have learned from the general discussion that looking straight into the ultimate statement tree here, we want to know, is the sample showing strong evidence that proportion of iPhone users is other than 50%. So this worded statement right here on Scratchwork, symbolically we can translate that into the statements as following. P, now other than means not equal to 50%, or equivalently in decimal, P is other than 0.5. This, to be clear, is an inequality. And so being an inequality, this is a statement perfect for our alternative hypothesis, H1. So in this case here, in this particular problem, our H1 says P is other than 0.5, and that's what we're trying to prove. And again, similar to how we have done and made our arguments in earlier examples, once we have identified our alternative hypothesis, we can now easily recognize or identify our null hypothesis by simply replace the inequality sign from the alternative hypothesis with an equal sign. And now we have created for ourselves or identified for ourselves the null hypothesis. But now, once we successfully identify the 2 hypotheses, H0 and H1 right here, and then we realize the situation we're looking at here is slightly different with those situations in the previous examples. So we have seen left tail and right tail when those inequalities were either less than or greater than correspondingly. But now our inequality is other than, meaning it could be less than or it could be greater than. And so this kind of inequality statement right here brings us into a testing procedure that's called a two-tail test. So just to be clear that our test we are about to be heading out for is being regarded as the two-tail test, unlike a left tail or unlike a right tail. This is a two-tail test due to that inequality being other than, meaning as a possibility it could be less than or it could be greater than, anywhere away from 0.5. And so now getting into the steps, again we need to look at the sample. So back in the reading of our problem itself, a sample of 423 cell phone users shows 321 of them are iPhone users. So right here, right immediately at the end of that first sentence, we understand that we have a given sample proportion. And this will be our evidence for the rest of the problem. In our sample of 423 cell phone users, we found 321 of them are being iPhone users. So this P hat in decimal, 4 decimal places, 0.7589. And again, unless being specified otherwise, usually I would go with the P hat value, sample proportion value, to be in 4 decimal places. And of course, our sample had sample size 423, that number in the denominator. And now, after realizing that we are using this sample of ours right here as evidence, then we must, again, keep in mind another understanding that the sample we have here is not the only sample existing out there. There are indeed infinitely many other samples out there at the same sample size. What we have here is only one among the many. And so in that way, the average of all sample proportion, where symbolically I notate by a mu p hat, this average here is the mean of all sample proportion values. So mu p hat in this case will be 0.5. And again, allow me to save the explanation of why and how I got this mu p hat to equal 0.5 at the very end, after we successfully put all the steps together and come to our final conclusion. The only connection I can see for now is our mu p hat is always equal to the value being claimed in our null hypothesis. And if you're looking back at the earlier examples, it has also been the same way. And so now, after having our mu p hat, another way of understanding this is it's the center of all sample proportion values. Now I'm looking for, as a next step, sigma p hat, which stands for the average spreading of all sample proportion values out there away from this center. Or formally speaking, it's a standard deviation of all sample proportion values. So calculation can be done by the following formula. Again, from the central limit theorem, 0.5 multiplied with 1 minus 0.5 divided by our sample size 423, and this expression is to be put inside a square root expression. And so final calculation comes out to be 0.0243. Again, the actual value from this calculation is a lot longer, but unless being specified otherwise, I usually go for 4 decimal places. So this value represents the average spreading, or the average spread for short, of all sample proportion values out there. Then once we had our sigma p hat value, the average spread of all sample proportion values, the next step now is again to calculate the z-score for our particular sample proportion value. So all these mu p hat and sigma p hat was to represent generally for all sample proportions out there, but now particularly with our sample we already had, then our sample is going to have a z-score. And again, optionally, I'm using a subscript p hat right here to indicate that our z-score is the z-score special for this particular p hat we're using. But the way to calculate z-score remains the same. 0.7589 is our actual value of our sample value. Subtract the center of the data, the mean value, and divide by the standard deviation, 0.0243. This z-score turns out to be, in 2 decimal places, 10.65. And again, the actual calculation can turn out to be a lot longer than this, but unless being specified otherwise, usually I'll go with 2 decimal places for any z-score. And this time I really have to emphasize that the z-score we have calculated here is a positive z-score. The reason I really have to emphasize that now is that after this point, we will be calculating the p-value as usual. And being a two-tailed test right here, it's going to be a little bit of a challenge to check whether our z-score is consistent with this two-tailed, because being a two-tailed test, this inequality can be a greater than or can also be a less than. So we don't need to carry out that checkpoint right now, but make sure you did make sure you do your z-score calculation correctly, and emphasize your sign of your z-score, the sign of your z-score clearly. But now, in the next step to calculate our p-value, we have a we have a decision making line right here. P-value. In this case, I am going to fire up a probability question. Find the probability that among all sample proportion, random variable capital P hat with a subscript 423. I want to find the probability where our P hat is greater than or equal. I am going to take a quick pause right here to explain, but why greater than or equal? Simply because our z-score is being a positive z-score. So think a little bit outside of the box here, but in other problems where you run into a two-tailed test and your z-score of the sample turned out to be a negative z-score, then here it's going to be a less than. So it could be a less than if negative z-score. Okay, so make a note of that before I move on. And now allow me to proceed. And so once again, as we are clear why we chose to go with this right tail inequality right here, then the value we place here is once again that sample value we already had. So 0.7589 is there to complete our symbolic statements of the inequality. But now simply this setup is only the right tail test, as we have seen back in our earlier examples. But keep in mind again, our test here needs to be done as a two-tailed test. So how can we make it a two-tailed test from currently being a right-tailed test? Whatever comes out from this probability, which we will eventually find, but we need to multiply that value by that probability value by 2. So 2 times, this is my multiplication sign here, 2 times the probability coming out from this statement. That's how we conduct any two-tailed test. And so at this point, anyone have seen enough how I explained about on the bell curve. So imagine that if we're on the bell curve, then again, the bell curve here has all of our sample proportion, P hat for 23. And so this particular inequality is indicating that if 0.7589 is somewhere on this bell curve, then I want to find the area shaded to the right-hand side. And once we found that area, this multiplied by 2 is indicating that we need to double that area. So it's sort of like we have 2 disconnected area on the 2 tails right here. And so the double of one single side is going to arrive at 2 equal sides. But that is the shading of our picture on the bell curve. And so, but in the end, as far as doing the calculation, it can easily be done by bringing ourselves back to the standard normal distribution. So this probability is the same as the probability on the standard normal distribution curve that we find a z-score greater than or equals 10.65. 10.65. But again, we must multiply that probability, or that probability for whichever that is, by 2. So 2 times our probability there. And so carrying on with the problem. So as far as the shading, this probability is equivalent to how much area shaded to the right-hand side. So I am going to run my LS&D program and provide z-score 10.65 to it. But once we found the answer to the LS&D program, this problem we're looking for specifically is about an area shaded to the right. So we make sure we must subtract the answer from the LS&D program from 1. But then at the end, we must multiply that probability by 2. And so in my next step, again, back on my computer screen, when I run with my LS&D program already open, with z-score 10.65, I am going to have the left area shaded, or area shaded on on the standard normal distribution curve, area shaded to the left-hand side is 1. Or basically this means some value that's literally speaking 1. So back in our problem, 1 minus 1, but don't forget to multiply all that difference by 2. Our final p-value comes out to be 0. And once again, in my style of writing, I write 4 decimal places for p-value. So in this case, 0.0000, I just want to emphasize that the value we have here, our p-value, is a value so small that even in 4 decimal places, it's still looking like a 0. So it's not really a hard 0, it's just a value that even within 4 decimal places, it's definitely a 0. And so now, once we found the p-value, then the next thing to decide, because remember, our role again, back on the computer screen, we want to decide whether or not our sample is showing strong evidence. So being strong evidence or not about our sample, we need to decide. And that decision there can be made by using the significance level, 0.001. And so back in our current problem, then with the p-value being 0.000 and our current significance level given, and notice even significance level we can change. In earlier examples, I was using only 0.01, but here I even use a smaller significance level. But we still have our p-value, even if we already double, still less than the significance level. And so, just like how we've been making our conclusion in the earlier examples, as long as our p-value falls below the significance level, then ultimately we can make that final conclusion that our sample, our p-hat value, is showing strong evidence. So we are showing strong evidence. But our strong evidence is to either you can use our strong evidence to reject h sub 0, or we can use our sample as strong evidence to support h1, our alternative hypothesis. And so, at the end, for the entire question itself, is the sample showing strong evidence that proportion of iPhone users is other than 50%, but ultimately speaking, the question itself is a yes or no question. And yes or no question, it looks for being strong evidence or not. So since we know that we just now concluded that we have strong evidence, so the answer to our question, the ultimate final answer to our question is yes, our sample is showing strong evidence. And let's now look at the detailed explanations for the steps in our testing hypothesis problem of example 4. And so now that we have identified the 2 hypotheses of our testing hypothesis problem in example 4, being h sub 0 stating that proportion of iPhone users is equal to 50%, or in decimal 0.5, and h1 is suggesting that based on our sample that generally the proportion of iPhone users should be other than 0.5. And so back in the steps, an inequality like this in our alternative hypothesis is being regarded as a two-tailed test. But I will give a clear explanation of why it's being regarded as a two-tailed test at a later point of our step-by-step explanation here. Okay, and so the sample we used in this testing hypothesis problem was a sample of 423 cell phone users, and we found 321 of them are being iPhone users. And again, in decimal, 4 decimal places, this sample proportion value is a 0.7589. And of course, this value in the denominator here is the sample size that we are currently using in our sample. So capital N equals 423. And so now again, that we have seen this idea so many times up to this point, as long as we can pick up a sample at a given size right here, then we must understand that there are infinitely many other sample values provided that we are in the same sample size here. So that means our p hat value is only one value among infinitely many other sample proportion values that I generally regard to all of them as a random variable capital P hat for 23. And so again, let me quickly write down the description of our capital P hat. So capital P hat as a random variable represents the proportion of iPhone users but in a sample of 423 cell phone users. All right, and so again, we have learned the idea from the central limit theorem that so now anytime we have a distribution, so this capital P hat subscript 423 is a distribution of sample proportion values. Then anytime we have, according to the central limit theorem, and anytime we are looking at a distribution of sample proportion values, then the average of all sample proportion values, because this random variable can have infinitely many different values, so the average mu p hat of all sample proportion values is guaranteed by the central limit theorem that must equal p, the population proportion. And further, average spreading, or formally speaking, the standard deviation, the population standard deviation of all sample proportion values must equal to the calculation that will come out from p times 1 minus p divided by the sample size and take the expression inside the square root. So that's just again a quick reminder of how we can find the average or the center of all sample proportion values as well as average spreading. All right, and now directly in our particular problem, the null hypothesis stated that p equals 0.5. Of course, right now we're testing this hypothesis. However, what if we're accepting that it was true? What if the statement was true? And so I'm going to start out with that argument similar to those we have done in example 1, example 2, and example 3 previously. If h sub 0 was true, we're starting out by accepting the value that's being claimed in the null hypothesis. And accepting it means for now we're pretending that our population proportion is truly a 0.5. And then let's find out what's going to happen. And so if h sub 0 was true, then consequently, based on what I have reminded earlier, then the mu p hat value must equal 0.5 as the guarantee as stated in the central limit theorem. And so we came up with this result as a consequence, but simply by applying the central limit theorem understanding. And so, and further, as a further consequence, average spread, or the standard deviation of all sample proportion values, now must be or can be found by taking a square root expression, and inside of that we're setting up 0.5 times 1 minus 0.5 and divided by 423. So I wrote these values in red simply to indicate that they are just simply the values that we are currently accepting as the truth. And then eventually we're going to find out, we keep searching for consequences of accepting this value being claimed in our hypothesis here to be the truth. And so once h sub 0 was accepted as the truth, then that value claimed in the null hypothesis became our center of all sample proportion values, as well as we can calculate the standard deviation of all sample proportion values by setting up this formula. And that's the whole reason of using our value 0.5 being written in red ink. And so calculation came out for sigma p hat here to be 0.0243. And again, I must mention again that unless being specified otherwise, normally in any of my lecture, when it comes to standard deviation of p hat value, I would go with the 4 decimal places in decimal expression. So the importance of these two values here, and they all came out from the central limit theorem, that this value here is the center. This can be regarded as the center of all sample proportion values. Our sample proportion is only one, and this is only one among infinitely many other sample proportion values. And so this is the center. And at this point in learning in a quarter, then anyone viewing this video should be well familiar with what it means by being the center of a data of a population. And from that center here, all values make some difference. So this is the average spreading of, because all values of p hats being spreaded away from the center. So this is the average spreading. The average spreading of all sample proportion values, or formally speaking, we call that it's a standard deviation of all sample proportion values. And now that we have the center and the average spread of all sample proportion values, again, realizing that our sample that we're having here is only one among infinitely many other sample proportion values at the same sample size, then a further consequence is that from where our sample stands, being 0.7589, so right from where our sample stands among all other samples, relative to the center here, we're going to take the difference. So 0.7589 minus 0.5 and divided by the average spread, 0.0243. This work is again going to give us the z-score of our sample. And so the work here is just the value of our sample, subtract the average, the center of all sample proportion values, and divide it by the standard deviation in the data. But now, since this work right here is a z-score work, but especially it's a z-score of my sample, so I optionally use again that subscript p hat to indicate that this is the z-score that I'm calculating for my p hat. Calculation comes out being 10.65, and I must emphasize that this is actually a positive z-score for our sample. So even though I have not explained what exactly it means by being a two-tailed test yet, other than just simply being able to decide by looking at the inequality here, but I have already mentioned in my steps that so anytime that we are about to do a two-tailed test, because it rang a bell right from looking at our alternative hypothesis, or somehow we are aware that we are running a two-tailed test, we are conducting a two-tailed test, then make sure we indicate the sign of our z-score clearly. And so now here in our problem, the calculation simply turned out to be a positive z-score. So I went ahead and emphasized the sign of my z-score by putting that in red ink. And again, with our sample being as large as 423, then with this sample size being 423, I am going to multiply that sample size with our currently accepted population proportion. So we still don't know what exactly our truthful population proportion value of iPhone users is, but currently we're accepting this. So with a sample being this big, taking the product with our currently accepted population proportion value, then the answer comes out to be 211.5, which is way above or well above 10. And again, I am going to take the sample size we're currently using and multiply with 1 minus 0.5. And recall again that it's all due to the reason that 0.5 is the value that we're currently accepting as the truthful population proportion of iPhone users. And so in that way, with our sample size being 423 being in product with this 1 minus 0.5 expression right here, we once again comes out with 211 as our final product right here, which is again a number well above 10. And so what I'm doing here is quickly to show that the sample size we're doing here as a reasoning, the sample size we're using here passes the requirements, the two requirements, in order for our distribution of all sample proportion values at size 423 to be on a bell curve. So in other words, I now can say this random variable capital P hat 423 is now normally distributed, and it would now take center 0.5 and the average spread that we have calculated previously, 0.0243. So we have now proven that all of our sample proportion values are on a bell curve. Then, among the steps that we have seen back in the earlier part of the video, then when it came to calculating the p-value, where the setup is find the probability of running into a sample proportion at size 423 being greater than or equal to 0.7589, and this probability is not only that, we must multiply that probability by 2. I have not explained why the setup is being done as so, but now with a setup being done like this, then we can calculate this value, this final p-value, as a bell curve problem, because now we know that any sample proportion is on a bell curve or comes out from a bell curve like this. And so now this probability by itself as a picture of the bell curve centering at 0.5, 0.7589 is somewhere, and then we're going to be making a shading to the right hand side according to the inequality. And again, I still have not explained why we're setting it up this way with the right hand side with the right tail inequality and multiplying the probability, the overall probability, by 2. But for now, as far as getting the value calculated, we can now proceed as a bell curve problem. And so this is truly just the same as on the standard normal distribution. Bell curve, we would be looking for a z-score. We would be finding the probability of having a z-score greater than or equal 10.65. And of course, we are multiplying that overall probability by 2. And so in that way, our final calculation for this p-value came out to be according to the steps everyone has seen back in the earlier part of the video, then this final p-value is 0.0000, meaning it's a value that in a very long decimal expression, then maybe at some value but small enough such that in 4 decimal places like this, it is still just like a 0, a very low probability, a very low chance. All right, so recall again that on any bell curve or a normal distribution, there is right around the center of the bell curve, there is a big fat area where we so call the common area. Indicating that these are the values that we commonly see being fluctuated away, being deviated away from the center. And outside of that common area, there are 2 unlikely areas on the 2 tails, 2-sided tails of the bell curve outside of the common area. And once again, we refer to those as the unlikely areas. Again, there's one being in red ink to the right hand side of the common area, or we call that it's the right tail unlikely area. And there's one in red ink outside of the common area being to the left or on the left tail of the bell curve. We can also refer to that as the left tail unlikely area. There are 2 areas, 2 unlikely areas outside of the common area. And so now, looking at our null hypothesis, where the statement was saying that the proportion of iPhone users equals 0.5. And further looking at this bell curve representing the distribution of all sample proportion values at size 423. If that null hypothesis was true, then consequently the value being claimed in our null hypothesis here, according to the central limit theorem, would become the center of our sampling distribution bell curve here. But now looking at our alternative hypothesis, the statement was saying that the counter argument here is saying that generally P is suggested to be other than 0.5. And so now this statement here with the inequality being other than, being not equal to, it means before we conduct picking up any sample, before we conduct any sampling and any testing of the hypothesis here, then the proportion, the actual proportion of iPhone users could be above 0.5. Or on another hand, again, according to the way how this statement is written in the null hypothesis statement, then the actual proportion of iPhone users could also be less than 0.5. 2 equal likely possibilities that can happen. And so now with our alternative hypothesis stating in that way, with an inequality being not equal to in the statement itself, and it means 2 possibilities can happen before we conduct our test, then generally speaking, when we now pick any sample and before we actually see our sample, then the sample itself can be either inside of the common area generally or being anywhere outside, but anywhere outside on the 2 separate tails here. So the idea of the problem now is that we generally we want to determine if any sample that we picked, it's just any p hat. Once we pick it up, would be likely enough to fall outside, all right, of the common area. Okay, so once again, generally we need to determine if p hat or any p hat would be in the outside of the common area. And what I mean outside here is the outside or in the area outside. Okay, be in the area outside of the common area. Okay, and so now a little more specific now. So in that way, because we're particularly interested in determining whether or not our sample would be falling into the area outside of the common area. But the area outside of the common area here, indeed, according to the picture we're having here, there are two areas. There's one on the left tail and there's one on the right tail. They're both being shaded in red color, and that is the reason why this kind of problem is being referred to as a two-tailed test, because one sample, but we trying to determine whether that sample, any sample we're about to have, would be likely to fall into any of the area outside. But we have two areas generally outside of the common area, and that's the reason why this kind of test, where the statement is having the inequalities saying not equal to the claim value, then we refer to that as the two-tailed test. And once again, it's all because we generally would like to prove whether or not we want to determine whether or not any sample that we picked would fall generally outside of the common area. And being outside of the common area, there are two tails that can equally happen. And now that I have just explained what it means by being a two-tailed test, but then usually, to make it simple and to make it easy for anyone starting into testing a hypothesis, let's say in our particular problem here, we have our null hypothesis stating that P, the proportion of iPhone users, equals 0.5. Then immediately, as long as we recognize this inequality in our statements of the alternative hypothesis, saying that P is not equal to 0.5 or P is not equal to the value claimed in the null hypothesis, that is already a good sign indicating that the testing hypothesis we are doing is going to be a two-tailed testing procedure, or in short, it's going to be a two-tailed test. And now I have to mention one more thing. So once we know that our test being a two-tailed test simply by looking at the alternative hypothesis here, then in that way, this is now an agreement, a convention among statisticians out there. But let's now look back at the wording of the problem being presented on my computer screen here. But so, just as usual, we have a significance level given, and the significance level here being as whatever written here, 0.001. But now the point here is that once we have identified that our problem is a two-tailed test, then the given significance level here is, so the significance level that we're looking at being specifically understood as a two-tailed significance level. And so my point I'm trying to make here is that as soon as we know right from looking at our alternative hypothesis that our testing hypothesis problem is going to be a two-tailed test, then the significance level given in the problem, the way how it's worded is just like any of the other problems. But now we must automatically understand that the significance level given here is a two-tailed significance level. And now, since I mentioned the term being a two-tailed significance level, let me now give a formal definition of what it means by being a two-tailed significance level. It's a little bit different than how I defined the one-tailed significance level that you have seen in earlier videos. So a two-tailed significance level given in a problem is simply defined as, it's a definition that came out as a convention among the statisticians. Any two-tailed significance level is the total area outside of the common area. And so I must underline this term right here. So the two-tailed significance level is the total area, just the complete total area outside of the common area. And so now, directly in our problem here, for example, again, let's look back on the computer screen, but we have a significance level given to be 0.01. So that means we must understand that this 0.001 right here is the total amount of area outside of the common area. So back on my picture, that means the total, the sum of these two little tails together must be 0.001 according to the given information, and according and combined with the way how we understand about the two-tailed significance level. And so that consequently means it's only a 0.0005 here and another 0.0005 here on each little tail here, because the sum, the total of these two little tails, it's the total area outside of the common area. So outside of the common area, there's always two symmetric areas to the left and to the right. And so two-tailed significance level is being the total area outside the common area. That means once we already knew that our total given significance level as a two-tailed significance level being 0.000 or 0.001, then each little tail here is only a half of that. That's a consequence that I was trying to point out right there. Now for a sample that, let's say if a sample that is found to be above the center, then for that sample we would calculate the p-value. Recall for yourself when we were still learning about the left tail or the right tail test, or generally as a one-tail test, then from wherever our sample can be. Let's say for example is being above the center, the claim in a hypothesis, in a null hypothesis, then the one-tail p-value is graphically represented as the black area shaded from where the sample is, but to the right-hand side. That's why it's called a right tail. It's also another reason why we're calling that a right tail, because we are shading to the right-hand side of where the sample is. So the p-value here is in black. And from there on, we let the calculated p-value to be compared with the significance level. We use the p-value as the black shaded area, and to compare that with the amount of right tail area being shaded to the right-hand side outside of the common area. So we're comparing that with the right tail area in red. And this right tail area in red right here I refer to as the unlikely right tail area. And so just like how we have learned, the p-value being in black shaded area, if it is smaller than the unlikely right tail area as in the picture right here, then clearly our sample would fall inside of the unlikely area, but to the right hand side or to the right tail unlikely area, then that means p hat value is one of the unlikely p hat values on the right tail here. And the way, and of course remind yourself again that the way to calculate the p-value there is to fire up the calculation where among all sample proportion values at size 423, we're looking for the value that's greater than, look at the black shading, we are shading from where our sample p hat is to the right hand side. So we want to shade from where our sample is and greater than or equal to our sample p hat that we found on this bell curve. But then imagine, on the other hand, the p hat's value can also be, once we found it, it can also be less than the center value, the value being claimed in the null hypothesis again. And so if that's the case, then the way we're calculating p-value, once again, as we have seen back in those problems when we were still doing left tail or right tail test, then the p-value was calculated as the area. Let's say here's our sample proportion value, and we were shading. The p-value was graphically represented by the area shaded to the left-hand side. And that's another reason why we're calling that it's a left-tail test, because we were creating an area shaded to the left of our sample value here. Once we found the p-value of that, then the p-value is once again is to be compared with the red area. And once we know that the black shaded area is being smaller than the red area, and this red area is the unlikely, but now this time left area, left tail area. And so if the p-value turns out being less than the value, the amount graphically represented by the unlikely red left tail area here, then once again we can say that our p hat would fall into the unlikely area on the left tail, or p hat would be among the unlikely p hat sample proportion values. But then either being a sample that is above the claim, or either we have a sample that's below the claim. What we have is only one sample. It can only tell the story about a one tail. So generally speaking, from where our sample is, the p-value we have been calculating throughout all problems in the previous examples is all about. The calculated p-value is to be compared with a, generally speaking, one tail red area. Either the red area to the right or the red area to the left here is a one tail unlikely. That's what we have been doing. One tail unlikely area, and the p-value as a black area, once it falls below or less than the one tail unlikely area, then we're saying that our sample falls into the particular sided tail. But now since we're in a two tail, and recall from what I have mentioned earlier, recall that in a two tail test, then the significance level is the total area outside of the common area. So common area is in here between the two red area. That's where we have the common area. Okay, and so that means each of the red tail here on the left or on the right is only half of your actual significance level given as a two tail significance level. And so that means any of the p-value we have been doing in a one tail problem, the way we're proving that was always about being to compare either less than or greater than, but it's only a one tail unlikely area. But being a one tail unlikely area is only half of the amount. Now when we're in the two tail situation, then it's only half of the actual amount of significance level, because as I have explained earlier, the significance level in case of a two tail test like this is being regarded as a two tail significance level, where it already represented the two areas, equal areas on outside of the common area to be totaled up to equal alpha here. And so that means each of the one tail here is only half. And so now seeing our alpha as a two tail significance level and looking at any of the one tail tests we have done, anywhere our sample stands in a one tail test, the p-value can only be compared with a half of the actual total significance level as a two tail significance level. And so now from this point on, mathematically speaking, we can just simply do a trick. that we multiply both sides by that 2 right here. Then, or in other words, seeing that as doubling, multiplying the 1/tail. So any of these calculation, any of these p-value I have been saying, they are all 1/tail p-value. So now all we do is if we double the 1/tail, p-value, then we are going to have a value that we can compare with the actual alpha, either being less than the actual significance level, 2-tail significance level, or being greater than the actual 2-tail significance level. Now back to example 4 on our actual bell curve representing the sampling distribution, or simply just the distribution of all sample proportions at size 423. We already knew that we had, if the claim in the null hypothesis was true, then we knew that we would have a center on this bell curve at 0.5. But then we found, in our particular problem of example 4, we found out that our sample was already a value being 0.7589, which is well above the claim here. And so now the p-value as a 1-tail p-value, yes, clearly p hat is here somewhere. So as a 1-tail p-value, we can calculate the p-value as the probability from where our p hat is, which is now in this case specifically we're looking for among all sample proportions at size 423. We'll be looking for the chance of having a p hat value greater than or equal 0.7589. But remind yourself, this is only a 1-tail test, and we use a 1-tail test simply because we only have one sample ever, and that sample, once we see it, we can immediately tell whether it's above or below the claim already. And so we go from a 1-tail test. And then this 1-tail p-value calculation, once we calculating it, yes, the p-value here, after the calculation, it went, the same as 1 minus the LS&D answer, and we already found our z-score for this sample was positive 10.65. And so our answer was a 0.0000. But this answer is now, again, I have to remind, this answer is only a 1-tail p-value. The red area to compare with this p-value here would be the red area only to the right hand side, outside of the common area, but only to the right hand side. And so that red area there, if we compare this p-value as a 1-tail p-value with the red area, then the red area in our case would be only a 0.0005, as I have explained earlier, because this amount of area here is only, this amount of red area is only half of our total significance level. And our total significance level given in a problem is being 0.001, as indicated right here in the problem as significance level 0.001. But in our problem here, it has already been decided to be a 2-tail significance level. And so this 1-tail p-value is clearly below this 1-tail red area. But unfortunately, the problem that we are doing is a 2-tail. And so to generalize the idea to arrive at a 2-tail p-value, so for the 2-tail p-value, then we simply just think about this 0.0005 right here as half of our given 0.001 significance level. Then it is the same as, this would be the same as, if we multiply both sides by 2 to make things a little simpler, then we're looking at 2 times our one-tail significance p-value, and then that's total. So now doubling this p-value would mean there would be another area in black right here, because our black shaded area is here, and doubling it means there's another area out there. Now we can compare our double of the one-tail p-value with our total significance level. That is going to be the final comparison that we want to arrive at. So it reads 2 times of 0, 0, 0, 0 is still less than 0.001 here, and this is now our total significance level, the total two-tail significance level. And that is the reason why among the steps where I was showing earlier, then calculating the p-value for a two-tail, I just went straight to setting up the right tail, because here our sample is already to the right hand side of our proportion being claimed in the center. So setting up the right tail test, looking for probability where p hat is greater than or equal to 0.7589. But then that p-value is only a one-tail p-value. The actual p-value for our two-tail test here, we have to just double it. And so in that way, just like that, among my steps, I was showing that finding the probability here is the same as finding the probability on the standard normal distribution curve, where z-score is greater than or equals to positive 10.65. But again, only doing this is a one-tail p-value. Our actual p-value here needs to be a two-tail p-value, and so we multiply that by 2. And so all that calculation among the steps eventually came out. We were doing 1 minus the answer from the LS&D program at given z-score positive 10.65. But then this total one-tail p-value must be double to ensure that this is the total, the final p-value for a two-tail test. And so, and our total two-tail p-value was at the end a 0.0000. And then that's how the p-value there was to be compared with the given significance level. In this case, already the total of all areas outside of the common area being 0.001. And so now having our two-tail p-value being less than 0.001, then again it's indicating that that our p-value, now in our case here, our sample is a sample above the claim, but this total two-tail p-value represents that even if when we pick the sample and the sample was a value below that, the total p-value, even if it's on the right tail or on the left tail, all together, two possibilities together. That's why we're doubling it. The total probability there is still being below or smaller than the total red area on the two tails. And that's why it's sufficient to say, that's why it's now enough to say that p hat, now we are ready for conclusion. P hat must be, generally p hat is among the unlikely values. And that leads to further saying that p hat is an unlikely value, meaning it's not easy to have a p-value, a p hat happening at this value right here. The chance to have something like this is among the only a 0.001 chance. That's the chance you get something like this. And so proving that our p hat is an unlikely value, that leads to, again, very similar arguments to the time when we were doing any of those one-tail tests. then we're saying that now p hat, our sample proportion, is showing strong evidence, or or itself is strong evidence. Okay. On one hand, to reject the null hypothesis in H of 0, or to support the alternative hypothesis H1.